Okay, so you ought to recognize this problem, right? It was from my friend's test the other day, and I was mumbling about how I think it was pi or n pi was not only the only solution to that quadratic, there are actually more and specifically imaginary ones. Well, we're gonna do that. So, we're gonna figure out all imaginary and real solutions to this quadratic in terms of sign. And well, I'm going to show you how you can find the imaginary ones in the first place. So first off, we're going to take a note. And what I'm talking about is complex definitions for sine and cosine. And I'll show you what I mean. What I mean is, let's go back to like the older videos where I was talking about complex numbers in their polar forms. Let's go back to when I derived the Euler formula, which is e to the I theta equals cosine theta plus I sine theta, right? So now let's do a little substitution. Let's actually no, not a substitution actually. Let's make we can do this. We can make the input negative, right? So let's make the input negative by doing this. So we can do e to the I negative I theta, because theta is now negative. We're basically like substituting for a new theta, and I'm using the same variable name. Yes, I know that. Yes, I know we're using the same variable name and making theta negative. That's really just that. And cosine of negative theta is the same thing as cosine of theta, because cosine is a even function, yes. Yeah. So cosine theta, it's symmetrical. You can just fold it, right? So the same sides. And sine is an odd function, so sine of negative theta would be actually the same as negative I sine theta. You can bring the negative to the outside because it's an odd function. So now we have two equations that we know are true and equal for all for all real numbers of theta. So what we can do is we can actually add them and subtract them and see what we can get. So let's actually first add the two equations. Here we have e to the I theta plus e to the negative I theta has to equal, when we add these two go away. That is 2 cosine theta, because you're adding two cosines. Divide the 2 on both sides. Cosine of theta in the complex world is the same thing as e to the I theta plus e to the negative I theta all over 2. Now let's do this. I'm gonna write it this way because I don't want to save space. And instead of adding them, let's subtract them this time. Change it up. When I subtract the two equations, I get e to the I theta minus e to the negative I theta has to equal cosine theta minus cosine theta is 0, so that goes away. This negative becomes positive because we're subtracting, and that becomes 2I sine theta. Now I can divide 2I on both sides, and I get sine theta in the complex world is equal to e to the I theta minus e to the negative I theta all over 2I. So now this is a complex definition for cosine, and this is a complex definition for sine. What this means is, if we rewrite taking the inverse sine as taking the inverse of this, right? We have a complex definition for inverse sine, and not only that, we can have a complex definition of tangent. If we just divide the two, or secant, cotangent, you can just go from here. And I would like to note that this does look really similar to the hyperbolic definitions, sinh, cosh, tanh. Yeah, I think there's a similarity based on that. So yeah, so now let's actually solve the equation. Okay, this time we're gonna actually do it fully. No more only real solution. That's for babies. We're doing complex too. So let's factor this. We get sine theta times sine theta minus 3 equals 0. Now sine theta equals 0. We don't need to use this complex definition. We have a real answer for that. So the solution set, that's just solution set. So solutions, that is n pi, where n is a integer, right? We talked about the other time. Now we also got to consider when sine of theta equals 3. So sine theta minus 3 equals 0, or sine of theta equals 3. So sine of theta equals 3. So now let's use complex definition for sine. So let's do that. Let me copy down. E to the I theta minus e to the negative I theta over 2i has to equal 3. And we're looking for theta. So yeah. So now we can multiply 2i on both sides. Right? Let's do that. E to the I theta minus e to the negative I theta has to equal 6i. Right? Now, here's the funky part. Let's multiply everything by e to the I theta while subtracting this 6i on that side. So let's do that. This is going to be a big step. So multiply everything by e to the I theta, and I'll show you why. This is going to be e to the I theta squared, right? We're multiplying them too. You can write that as e to the 2i theta, but let's write that as e to the I theta squared. I'll show you why. Now, this just goes to -1 because these are inverses of each other, so this is just -1. So let's write -1 over here. My marker is slightly failing me, sorry. So -6i goes on that side. Here we have 0. -6i on that side times e to the I theta. So that is going to be minus 6i e to the I theta. Now, if you're truly vigilant and you're good at mathematics, you will notice that this is what? A quadratic. Something is squared times something, this 6i is a constant, minus another constant that is 0. We can use quadratic formula to find out the solution for in terms of e to the I theta. So let's do that. Let's write this here. Marker's failing me. E to the I theta. Oh my god. E to the I theta. So quadratic is -b, which is 6i plus minus the square root of plus or minus the square root of 6i squared b squared, which is -6i squared, or just -36, right? Yeah, -36, because -1 squared is 1, 6 squared is 36, I squared is -1, so -1 times 36 is -36, minus 4 times a times c, right? 4 times a is 1, so we don't have to worry about that. 4 times -1 is -4. There's a negative over here, so that's actually plus 4. All over 2a, which is just 2. Right? -b plus or minus the square root of b squared minus 4 times a times c. Yep. Let's simplify the inside. Let me do that real quick. -36 plus 4 is -32. So let's just write that as the square root of -32. Right? So now we have this. Let's do some simple, algebra to figure out the rest. Let's take the natural log of both sides. And then let's also divide I on both sides, which is actually the same thing as multiplying by -i. Right? Let's multiply both sides by -i. So we have theta equals, let's see here, natural log of 6i plus minus the square root of -32 over 2 times -i. Right? Guess so. And also keep in mind this is actually an angle, which means that what you can do is you can actually add 2n pi, where n is an integer. Basically, because like technically pi over 6 and 13 pi over 6 are the same angle. 0 and 2 pi basically work as the same angle, just going one revolution. So that's what 2n pi means, you're going one revolution around. Also, if you want to do more simplifying, actually, there's something you can do more. So let's remove the 2n pi for now, because I don't want to write that over and over again. So, if you felt uncomfortable with the fact that there's an I inside the natural log, and natural log doesn't even work for negative numbers, let's fix that. So theta equals I. Let's make this the same thing as plus or minus I square root of 32. That's what I means. So I'm going to factor in I at the same time. So we're going to get ln of I times, that's going to be 3, because you're dividing 2, right? Plus minus is 1/2 square root of 32, right? Negative I. So now we can use log properties to break them apart. So let's do that. Oh my god, this thing is killing me. I need a new marker. Theta equals negative I times natural log of I plus natural log of 3 plus minus 1/2 square root of 32. What is natural log of I? It's not that difficult to figure it out, actually. Let's go to polar form of I. So polar form is you need the radius, I need the angle of the complex plane. So this is 1, this is -1, this is negative I, this is I. Angle is pi over 2. Radius is 1 because you're one step away from the origin. So I actually equals e to the, no, which is, yeah, r is 1. So e to the I pi over 2, right? Because you're going that way. So basically when you take the natural log of both sides, natural log of I actually just equals I pi over 2. That's something so beautiful of the complex numbers and why they're actually so useful. And if no one tells you this, is that they're something we call a closed set, which basically means you can throw anything in there, right? Any complex number in there, and the worst you can get is another complex number. You can't do that with the real numbers. If you throw a negative number in the square root, everything breaks down. Negative number in a natural log, everything breaks down. Number with absolute value is bigger than 1 in a sine or cosine function, it breaks down. So yeah, that's what's so useful of the complex numbers. It doesn't deal with any BS. It just stays in the system. You can do a lot of stuff with complex numbers, and that's why it's very useful. So yeah, let's continue. Theta has to equal, okay, negative I times I is 1. So let's just write down pi over 2. Negative I over there, so minus I natural log of 3 plus minus square root of 30. 1/2 square root of 32 over 2. That square root of 32 is outside, not inside the 2. So yeah. Now we can add a 2n pi because this is technically an angle, right? And you can copy it over where n is a integer, right? And let's copy that one. That also comma n pi. Since we already have n is an integer, let's write comma n pi, where n is an integer for both of them. Yeah, so this is your final solution set for sine squared x minus 3 sine x equals 0. So yeah, pretty interesting.